So again, in this session, we're looking at polarity, molecular geometry to try to strengthen these concepts. And so here we want to identify the following compounds to see if they're polar or not. And we have TeO3, ethyl amide, we have, what is that? Butene, aluminum fluoride, dimethylthile, Tellurium Tetrachloride, and CF3CH3. Now, some of these are organic compounds, some of them are inorganic compounds. And you may ask, well, I've never seen a compound, organic compound with sulfur, but you have seen a compound with oxygen. So if we write this with oxygen, see, oxygen and sulfur are in the same group, so they're going to have similar bonding in organic compounds of each other. So if oxygen bonds a certain way, sulfur would also mimic that bonding as well. So now what you need to do is first draw the Lewis structures. And so here I've drawn all the Lewis structures very nicely. And so we have TeO3. Now TeO3 you may have never seen before, but it's synonymous with SO3. Because again, if the central atom is in the same group, they're going to have similar, similar Lewis structures. And so here at TeO3, it has one double bond oxygen to single bond oxygens. Now this has resonance, so this double bond can alternate back and forth. And we get this 3 bonding pairs around the central atom. And so here, with 3 bonding pairs, no lone pairs, this is trigonal planar geometry. And so trigonal planar geometry means that the dipoles on each set of bonds are going to cancel out because they're all symmetrical. So this would be a nonpolar compound because again it's trigonal planar. If it's trigonal planar, the dipoles are arranged in such a way that using geometry they cancel out with each other. Next we have ethyl amide, and this is the Lewis structure, so CH3, CH2, NH2. Whenever you see it written like this, the hydrogens are attached to the the non-hydrogen atom before it. So there's 3 hydrogens attached to the carbon, and then this carbon is attached to this carbon, and then there's 2 hydrogens attached to this carbon, and then that carbon is attached to this nitrogen. And so already by looking at this structure, you can kind of gauge whether it's going to be polar or nonpolar. So if you see here CH3, CH2, remember the CH bonds are nonpolar. Oh, snap. So this side of the molecule has nonpolar bonds. However, this side of the molecule, NH2, now here nitrogen has 3 bonds, 1 lone pair. This nitrogen is trigonal pyramidal. This is polar. So overall, this is a polar molecule. And if you ever see a molecule that looks asymmetrical, typically it's going to be polar. So you see here we have an NH2 on one side, we have CH groups on the other side. This is asymmetrical, so it's a good indication it's going to be polar. So groups like NH2, OH groups, carbon double bond oxygen, these are good polar groups to have on an organic molecule. So this is polar. We go to the third example, 2-butene. So here notice that all the bonds are nonpolar bonds. So we have CH bonds, we have CC bonds. These are all nonpolar bonds. So this is going to be a nonpolar molecule. And in just for your reference, anytime you see a pure hydrocarbon, so a pure hydrocarbon only contains carbon-carbon, carbon-hydrogen bonds, those are always going to be nonpolar. So anytime you see a pure hydrocarbon, again, pure hydrocarbons only contain carbon-carbon, carbon-hydrogen bonds. These are always going to be nonpolar. Next, we go to aluminum trifluoride. Again, here, if we look, aluminum has 3 bonding pairs of electrons. So this is going to be trigonal planar. Since it only has 3 bonding pairs of electrons and there's all 3 fluorines around aluminum, this would be nonpolar as well. Next, we get to dimethylthile, or excuse me, dimethyl ether. I apologize, that's the correct name. And so the sulfur behaves just like oxygen would in an organic compound. And so remember we talked about in the previous session that oxygen likes to have 2 single bonds and 2 lone pairs. Sulfur, the majority of the time, not always, but most of the time, it likes to have, if it's a thioether, likes to have 2 single bonds and 2 lone pairs. So this is the Lewis structure of this molecule. Now you may say, well, hey, a CH bond is nonpolar and a carbon-sulfur bond is also nonpolar, because if we look at the electronegativity difference between carbon and sulfur, 2.5 minus 2.5, it's 0. So this molecule contains only nonpolar bonds. However, notice on the sulfur that there are 2 lone pairs of electrons on the sulfur. And sulfur, if we just look at the sulfur atom, sulfur has a bent geometry. So since sulfur has a bent geometry, those lone pairs on that sulfur don't cancel each other out. So this would be a polar molecule. Next we have tellurium tetrachloride. Here we have 4 bonding pairs and 1 lone pair of electrons. So again, not even knowing the geometry, just by looking at this molecule, we see that, hey, this looks asymmetrical. We have 4 bonds and 1 lone pair. And so this should be a polar molecule. And in fact, it is, because the geometry is seesaw. And seesaw, when you have 4 bonds and 1 lone pair, seesaw is a polar geometry. Next, we have CF3CH3. Now again, the carbon here has 4 bonds, it's tetrahedral, and the carbon here is 4 bonds, it's tetrahedral. However, since it's not the same groups on both sides, one has 3 fluorines, one has 3 hydrogens, this is asymmetrical, so this would also be a polar molecule. So again, if something looks symmetrical, typically it's going to be nonpolar. If something looks asymmetrical, generally it's a polar. So this question I like, because these are the types of questions you may see on an exam. It gives you an ion or molecule, and then asks you a series of questions based off of this ion or molecule. So here we have the ion SF3-, and we want to answer the following questions. How many lone pairs of electrons on the central atom? What's the electron geometry of the ion? Molecular geometry. what types of bonds are present, and which element has the -1 formal charge. So you can do this by using that shortcut because it's a central atom bound to the halogens. So you can't do that, but I'm going to draw the Lewis structure for you to show you what it looks like. And so this is the Lewis structure of SF3 minus. It has a total of 28 electrons. And so the number of lone pairs on the central atom are 2 lone pairs. What is the electron geometry? So we have a total of total electron pairs is 2 lone pairs plus 3 bonding pairs equals 5 electron pairs. So when you have 5 electron pairs, the electron geometry is trigonal bipyramidal. Now it's very important that you remember the electron and molecular geometries. Now what's the molecular geometry? Well, we have 2 lone pairs and 3 bonding pairs. And you'll notice here that the bonding pairs form a T shape. Hence, this is T-shape molecular geometry. Now, what types of bonds are present? So here you would have to go and, of course, on an exam or quiz, we'll give you electronegativity values. But here you could have used your book or the internet if you were following along and calculate the electronegativity difference. So we're looking for the difference in electronegativity between sulfur of fluorine bond. So fluorine, we all know, has electronegativity of 4. Sulfur has an electronegativity of 2.5. So this has an electronegativity difference of 1.5. So this would be categorized as a polar covalent bond. The next question asks which element has a -1 formal charge. So we need to calculate the formal charge of both elements. So we have fluorine, 7 valence electrons minus 1 bond plus 6 lone electrons is 0. So each fluorine has a 0 formal charge, and sulfur, 6 valence electrons, 3 bonds plus 4 lone electrons, has a -1 formal charge. So the sulfur atom has the -1 charge. However, this species here would be unstable because the negative charge is not on the most electronegative element. So this would be a very unstable ion because formal charge rules like to have the negative charge on the most electronegative element. So here, instead of an ion, we have a molecule, IBr5. Answer the following questions. How many lone pairs of electrons on the central atom? What's the electron geometry of the molecule? Not ion, sorry. Copy and paste there. What's the molecular geometry of the molecule? This should be molecule. And then what types of bonds are present? So again, you can do the shortcut. We have a central atom bounded to halogens. So you can find the total number, take the number of bonding pairs, multiply by 8, subtract that from the total, and I'll tell you the number of lone electrons on the central atom. But I'll show you using the Lewis structure. So this is the Lewis structure of IBr5, and you'll see from the Lewis structure, we have 5 bonding pairs and 1 lone pair. Total of 6 electron pairs. So if we have a total of 6 electron pairs, the electron geometry is octahedral. I jumped the gun. We'll put this down here. And so we have one lone pair on the central atom. Now for the molecular geometry, again, we have 5 bonding pairs and one lone pair. So this would be a subset of octahedral subset. And so this would be square pyramidal geometry. Now, what types of bonds are present? Again, you have to look at the difference in electronegativity. We're going to look at the difference between iodine and bromine. So bromine is 2.8, iodine is 2.5. This would have an electronegativity difference of 0.3. So the iodine-bromine bond is a nonpolar bond. However, even though we have nonpolar bonds in this molecule, since we have this lone pair of electrons, this is actually a polar molecule. So even though we have nonpolar bonds, but since we have this lone pair of electrons on the central atom, this makes it a polar molecule because that lone pair doesn't cancel out. So that is one of the ways you can have a polar molecule, is where lone pairs don't cancel each other out. Now here with organic molecules, you can have what are called geometric isomers. And geometric isomers, what they are is the same compound, but they're just arranged a little bit differently based on the way the groups, for example, are arranged around the double bonds. And there are 2 types of geometric isomers. We have cis, which groups are on the same side. Of the double bond. And we have trans, in which groups are on different sides of the double bond. So you have to have different groups in order to have a cis and trans isomers. And so we want to know which of the following molecules would have the largest dipole moment. So the first thing we can go through is we can go through and identify if there are any nonpolar molecules present, because remember, nonpolar molecules will have a 0 dipole moment. And what should stick out right at the first is number 2, because you notice number 2 is a pure hydrocarbon. And pure hydrocarbons, as we said earlier, are nonpolar molecules. So if it's nonpolar, it's going to have a 0 dipole moment. So it can't be number 2. Now if we look at, we have 1, 3, 4, and 5 left. Now if we zoom in on 5, we notice that we have, hydrocarbon group here, hydrocarbon group here, hydrocarbon group here. So all 3 of these are nonpolar groups. Now this iodine, we have to decide, is the carbon-iodine bond a nonpolar bond? And in the previous session, we actually looked at this bond. And if you notice, the electronegativity difference between a carbon-iodine bond is 0. So this is also a nonpolar bond. So since this contains all nonpolar bonds, this is also a nonpolar molecule. So it has a 0 dipole moment. So again, the way I know it's nonpolar is because it contains 3 hydrocarbon groups. So those are automatically nonpolar. And as we saw earlier in an earlier session, the carbon-iodine bond is a nonpolar bond. So since this contains all nonpolar bonds, it's a nonpolar molecule. Therefore, it has a 0 dipole, and I spelled dipole moment wrong. I apologize. It's Friday. Dipole moment. So now we've narrowed it down to 3 choices left. So we need to identify which of any of these are polar molecules. So if we look here, notice in number 1 that the 2 chlorine atoms are on opposite sides of the double bond in number 1. In number 3, we only have 1 chlorine atom. And in number 4, we notice that the 2 chlorine bonds, or 2 chlorine atoms, are on the same side of the double bond. And remember that the dipole moment is pointing towards the chlorine. So now notice here in number 1, this is called a trans isomer. And the reason it's trans is because the chlorine groups are on opposite sides of the double bond. And notice that if we overlap these 2 dipole moments, the positive end of one will cancel out the negative end of the other. So whenever you have a trans isomer, these are nonpolar because it has a 0 dipole moment. So trans isomers have 0 dipole moments. They're nonpolar because the dipoles cancel out. Next we have number 3 and number 4. The only difference is in number 3 we have 1 chlorine group. In number 4 we have 2 chlorine groups. And so number 4 is called a cis isomer. Cis isomers have a non-zero dipole moment and are polar. So again, whenever you're comparing cis and trans, trans is nonpolar, cis is polar. Now we've got to see which one of these 3 or 4 has a larger dipole moment. And since 4 has 2 chlorine groups, we know that this side of the molecule is going to be negative, this side is going to be positive. Whereas in number 3, we just have a little bit of negative because only 1 chlorine group here, and then we have a big positive, or we have a positive side as well. But since we have 2 chlorine groups, the difference in the sides of the molecule is very well defined. So this has a greater dipole moment in this direction. So number 4 would have the largest dipole moment. And then number 3 would have the second largest dipole moment. The others would have a 0 dipole moment. Just looking at the molecular geometry, and here we have an organic molecule, and we want to determine the molecular geometry of the ones we have labeled. Now remember, with organic molecules, we're only going to go up to 4 electron pairs. So everything should be between 1 and 4 or 2 and 4 electron pairs for molecular geometry. If we look at N1, we have 1 lone pair and 2 bonding pairs. So N1 is going to be bent molecular geometry. We look at C2. C2 has 1, 2. Now remember, double bonds count as 1, so this has 3 electron pairs, and they're all bonding pairs, so C2 is trigonal planar. Next we have O3. So O3 has 2 lone pairs 2 bonding pairs. So this would be bent molecular geometry. S4, now sulfur has 1, 2. Now the double bonds count as 1 pair, 3, 4. Sulfur has 4 bonding pairs. This is tetrahedral. And lastly, N5, we have 1 bonding pair here. Now these 2 hydrogens represent 2 bonding pairs. So that's a total of 3 bonding pairs and 1 lone pair. So this would be trigonal pyramidal molecular geometry. Notice that all of these, there's no more than 4 electron pairs total for each one.